In this lesson, I'm going to focus primarily on what it takes to enable machine learning. We know there's an embedded systems component and there's a machine learning component. And this combination is really what makes TinyML come out of. Now let's go back to our favorite example of OK Google, right? Where we have a Google Assistant and the device. The assistant being the virtual machine learning part of it, and the device being the physical component. Now, when we say, OK, Google, the machine wakes up. Let's break this process down into three fundamental steps that are there. The first step is that there is an input that's coming in. The input is an audio input because you're saying something, and then the machine is effectively picking up your audio signals. Then there's a certain bit of processing that's actually happening, which is actually figuring out what you are trying to communicate. Did you actually, in fact, mean to say, OK, Google, for instance? And then there's the response that comes out where the machine physically generates some sort of output. It might be lighting up the lights of the device to say that it's actually heard you. For instance, on Alexa, you see a blue ring that goes above the top. In Google devices, some sort of light shows up usually. That's an actuation of the system responding back to you. The three fundamental steps are input, process, and output. This is fundamental to any embedded system, and it's also true for any machine learning system. That said, let's try to understand each one of these in greater detail. So what kind of input can we have? Well, the critical thing about TinyML is that it's all about sensors. There are many, many different kinds of sensors. There are motion sensors, there are acoustic sensors, there are environmental sensors, proximity sensors to say if there is someone close, if you're holding your phone close to your face. There are image sensors, and there are force sensors, lots of different kinds of sensors. I'm just showing you a general sprinkling of the possibilities here. In the particular example, OK, Google, for instance, it's an acoustic sensor because it's a microphone that's actually picking up the signal. You might have biometric sensors, for example, things that detect your fingerprint or your heart rate. So you can take these heart rate signals and actually do a lot more with them. Here are two examples I'm showing you. One is a medical device like a glucose monitor from UC San Diego. That's a simple little device that can stick on your skin and tell you what your glucose level is, which is critical for certain patients. Or you can have EKG, heart rate sensors coupled with PPG. I can't even remotely try to pronounce that word that's on the slide right now. So I'm not going to try, but I'll give you a chance at it. Effectively, PPG is a means to actually analyze the changes in your blood conditions just by looking at the light and how the light moves through your skin and hits the blood vessels. So if you had these kind of devices which are inputs, then you can take data and do intelligent things with it. Now, there are also other kinds of sensors like image sensors, for instance. The image sensor that comes with your kit is a small little camera with it's actually a pretty high resolution camera that interfaces with your microcontroller, and you can use it for computer vision. Now, you get all that data that's coming in from a sensor and sometimes from multiple sensors, and you have to process it. How do you process it? Typically, in order to run machine learning, you need big processors like the big TPU or GPUs we spoke about. Now, that's conventionally how people have been thinking about machine learning. Big data, big systems. It's a complex workload, so it means big computing horsepower. OK, well, what does big really mean? Let's use a proxy here for indicating what is big and what's small. Well, let's look at the amount of area that it actually takes for the processor, the brains of the actual system, right? If you look down here, the big processors are on the order of over 500 millimeters squared. That's the effective area, of the chip that you're looking at. Then let's talk about something smaller, like your phone, for instance. If you look at your phone, the A12 biometric processor from Apple, for instance, is much, much smaller, right? And it's only 83 millimeters squared, significantly smaller than the big GPU, for instance. Then, of course, you have your smartwatch. And the smartwatch processor is even smaller. And now we're starting to go from big to small to tiny. But we are not quite there yet. Let me show you something quite fascinating. We're just getting started. Are you ready for this? Look at something really small like this KL03 processor from Kinetis. It's 3.2 millimeters squared. I really want you to go out and get a ruler right now and try and draw an area of 3.2 millimeters squared. It's a really, really small processor and consumes very little amount of power. In fact, it's a very small processor because it has very little memory and very little compute. And we'll be talking about all these things at a level deeper in the next set of videos. But before we get there, the context that I'm trying to get to you is that machine learning is typically thought to be run on big systems. And now we're talking about these tiny kind of systems over here. Just to put this into perspective of this little processor sitting on a golf ball, okay? So you know how big a golf ball is, right? And then you know what? How small each of these dimples on the golf ball are. It's smaller than a dimple on a golf ball. So it's really, really small. And that's what the point I'm getting to. And if it's that small, can you imagine putting it virtually anywhere? You won't even notice it, right? So, well, now here's the wham bam. There are over 250 billion of these kinds of small little processors everywhere in the world. They're called MCUs or microcontroller units. They're pervasive, they're already here, they're everywhere. They're inside our automotive car, inside your washing machine, inside your iron, your coffee maker, everywhere, right? And now the question is, can you make them smart by putting tiny machine learning on top of it? So let's talk about these small little processors. If there are 250 billion today, there are going to be many, many, many more of them coming in the next few years. And now this plot on the x-axis shows you the years and the y-axis shows you the millions of units, right? That's in 30,000 million units there that are getting shipped. So now look at the projected forecast values. These things are just going to continue growing. The demand for microcontrollers in the world is insatiable because we are building so many new devices now. And we're going to see this as increasing as a trend. And what's going to happen? Is the price going to increase or decrease? Well, as the volume of these microcontrollers starts to increase, it's fundamental economics. The price will drop because they're so pervasive. So the manufacturing cost effectively goes down. That's why this plot, that's what this plot is trying to show you, that the price of a microcontroller is going to go below 50 cents. It's almost like going to be, super, super cheap as the trend continues for the rest of the decade. Once you put this in context of what these devices are capable of doing, especially when you enable TinyML on top of that, and with these super cheap, pervasive devices, it's going to be incredibly exciting. So what's so interesting with these devices is that they consume very little power. To put things in perspective, a GPU like the one I showed you before consumes 300 watts. And you need to plug that thing into a serious wall connector. Now, as you go into something small like the processor that's inside your phone, for instance, well, it consumes significantly less power. It only consumes about 3 watts. That's 100x smaller. And when you go into microcontrollers like the sentient processor that we're looking at here, well, we'll actually come back and learn a bit more about these in more detail. The machine that consumes only 140 microwatts. That's astoundingly small. And this is what tiny machine learning computers are all about. It's all about consuming milliwatts or microwatts or less. And so these are very specific concrete numbers of what the future is holding. So imagine if these processors consume so little power, then we might actually be able to run them on coin cell batteries, because a coin cell battery is going to look very, very big compared to this tiny little processor. And that's what the potential we're talking about. And then there's the processing part. Now we've come to the input. Let's say you take some input and you process it, and now you need to generate some output. What kind of output can a TinyML device do? Well, you can have a physical actuation, like activating servos, for instance, or you might be able to trigger speakers, generate some kind of signal. In the case, okay, Google is effectively, what you're doing. The machine is waking up and might say hello or to something of that effect. But it's not always about physical actuation of the devices. You can actually also have digital actuations. In other words, you can do some input processing. You can extrapolate some kind of interesting data. You can send a digital signal out to the screen and actually show some useful information. So what are microcontrollers really enabling? Well, fundamentally, it starts from the fact that microcontrollers are really small and they're very pervasive. Second is that they consume very little power, which makes them really practical to deploy, for a long, long time and have little or no batteries. And so you don't need to tether them. You don't need to keep recharging them. And then they're really, really cheap, which means that they can be everywhere. And given that we're just starting to build more of these devices, the demand is only going to go up from here. And if you put machine learning on them, we're going to uncover a whole new set of applications. And that's the beauty about it. By building these small, tiny embedded systems and coupling them with machine learning, which we'll talk about more soon, and putting these together, we'll unlock TinyML. So what I want you to take away from this particular lesson is that microcontroller units are these small, tiny processors that are fundamental building blocks of TinyML. Okay, that's number one. Number two, these devices are going to be pervasive or ubiquitous because they are very cheap and there's going to be a very high demand continuous over the next decade. Number three, the question is, are they capable of running machine learning models in them? We'll be getting to that in the next set of videos, and I'll see you soon.